Okay, so thanks for joining. Good afternoon, everybody, and thanks for the opportunity I was granted to present a couple of thoughts about control valves. So I'm Galik. I'm graduated at the Technical University of Budapest, Hungary as a mechanical engineer. I joined Emerson in 2005 as an internal sales guy at the Hungarian sales office, sizing, selecting control valves. Then in 2008, I get a job in the UK, power application engineer for Europe with Fisher Control Valves business unit. That brought me to Chatham, UK. Then later it's involved to business development manager. So apart from helping sizing, selection, difficult control valve to the sales people, also I try to help them to identify the opportunity in the industry. And since 2023, I became the technical sales manager for Emerson Fisher Control Valve UK and I, so not European responsibility, but my scope improved with other industries as well, not just power. So control valves are there in every industry. There are in power, in refinery, in dispatch. Each and every unit has a process diagram, something like this with multiple control valves, upstream, and also in chemical industry. Now you might consider these control valves like pressure, flow, or temperature, or level control valve, but in a truer sense, ultimately they have much more important role. They make sure the process is running efficiently. In certain application, they are protecting valuable equipment, avoiding unplanned shutdown, minimize repair cost, or provide safety. Bear in mind, each and every individual control loop has impact on the site key performance indicators like overall profitability, sustainability, and safety one way or another. Now, control valves come in different style and shape and form and size and material, obviously, but there is one common feature which is true for every control valve, which is that the control valve is always sitting in the control loop, right? There's no control loop without control valve or other way around. So in the control loop, you've got a sensor, a transmitter where you measure the process variable, what you are trying to control. You've got a controller which compare the measurement and the set point, and then sends a signal to the control valve to act. The performance of the control loop can be described how strictly can follow the set point. So in this graph on the right, the desired value at the bottom is pretty, basically the value what you would see at that point of the process. Now, if your control loop performance is bad and cannot follow the set point very closely, just like this badly, you must move your set point far away from the desired value, and basically to make sure you, in this case, don't go below that. And basically, the farther you are from the desired value, the less efficient you are. Now, if you can improve the behavior of your control loop, and now it can follow the set point more closely, you can move your set point closer to the desired value, improving the efficiency. But the big question is, where is these bad performances coming from? Based on industry investigation, it's been found that 35% of the root causes is coming from the control strategy, and you see that people are spending a huge amount of money for better controller, for better control system, for tuning, and also on and so forth. But 28% of the root causes are down to the final control element, down to the control valve, which is probably shocking, especially because I met too many people who thought the most important feature of a control valve is a face-to-face dimension. Well, it isn't. If you're surprised, let me put it a little bit easy way. So let's say the transmitter is my ear, right? And I've got a perfect pitch, right? And the controller is my brain, and I'm just a great music composer. Still, with a hand like mine, I won't be a guitar hero. Simple as that, because my final control element isn't good enough. If you make it a little bit more engineering, the accuracy of the sensors can be very good, There's no point really to talk about accuracy when it comes to the controller. But when it comes to the accuracy of the controller, that can be bad or even worse. Which means if you really want to improve your control loop performance, the control valve is a guide to really look at. And again, the site performance, overall performance, is driven by individual control loop performances. So the big question, where is this bad performance coming from? For that, we need to go a little bit deeper. So the first thing to understand, what is the gain? So basically what you would like, that if you change the output on the DCS, your control process variable, in this case the flow rate, would change accordingly, and the amount of change would result in the same amount of change on the control process variable. So the gain between the DCS output and the process variable would be 1 all along the control range. But in reality, when you change the output on the DCS system, you basically make the control valve move upper or lower on the travel, and the control valve has his own called inherent characteristics, which is the measurement in CV. So CV1, basically 1 gallon per minute water through a restriction with 1 psid constant pressure difference. So this inherent characteristic measured that you apply 1 psid pressure difference on the valve, starts to open and measure how many gallon per minute of water you've got. The valve inherent characteristic could be equal percentage, like in this case, or linear or quick opening. Now this valve is sitting in the process, and the process also has his characteristic. The process characteristics, one hand coming from the inlet pressure based on the pump curve, and the pump curve says the more flow rate you want from me, the less pressure I give you, and the outlet pressure of the control valve coming from the system after the valve, which says the more flow rate you want to push through, the more back pressure I give you, which means that as the flow rate changes or increasing, the available pressure difference on the valve is changing. So basically, these blue curves try to represent this kind of characteristics. Now, if we now grab the basic flow rate equation, which says the flow rate is equals the CV multiply the square root of the pressure difference on the valve, right? We will end up with some flow rate, this red line. Flow rate changes across the travel range. Now, the gain between the DCS output and between this red line obviously won't be constant 1 all over the entire control range, but you can have good controllability as long as the gain is between 0.5 and 2. If it's lower than 0.5, you will have a very sluggish reaction. If it's higher than 2, 3, 4, or even more, you will have a very nervous controllability, over and undershooting all the time. Now, in this case, in this scenario, this installed control valve is just perfectly fit to the process. However, if we replace now this valve with an oversized valve, which has an inherent characteristic much bigger and goes up till Aberdeen, right? What you can notice that the compensation capability at the bottom towards the changing pressure difference is not much there. So you will end up in a flow response at the low area, very high gain, and a high area, very low gain, and only some small part in the middle where you can actually properly control. Well, with a linear inherent characteristic can cause the same issue. Probably you heard people tends to say that, for instance, butterfly valves, which typically has linear inherent characteristics, you can only control between 30 and 60 degrees of opening. This is exactly the reason why is that. On top of that, oversized control valve just cannot provide fine control and suffer from low opening operation. So gain is one part of the story. The other part of the story is the nonlinearities. So basically, again, in an ideal world, as you change the control signal, the valve would start to open and go to fully open. All right, but in reality, when you start to change the control signal, the valve won't move at the beginning and then go open. And if you are coming down, again, it's not moving and then comes down. So you end up with hysteresis, a dead band. Now, the main sources of the dead band are frictions, packing frictions, other frictions inside the control valve, and loss motions. Loss motion can be inside the valve body. For instance, if you have a pilot plug balanced construction, then the valve stem and the main plug doesn't move strictly together. So there is a loss motion possibility, or between the valve and the actuator, or inside the actuator. For instance, if you get electric actuator with a lot of gearboxes in there. And the role of the positioner to detect the difference between where the stem should be and where the stem real position, and do some correction, apply more or less pressure to the diaphragm on a pneumatic actuator, or rotate the motor of the electric actuator. Now, dead band can be reduced, but cannot be completely eliminated, and it's measured as a percentage of the total travel. And here comes the trouble, because dead band cause position deviation will be multiplied by the gain that will result in flow deviation. Just an example. So for instance, we've got an oversized valve with 100 millimeter long travel. And actually this valve isn't that bad, because it has inherent dead band only 1%, which is 1 millimeter, right? However, this valve uses only the bottom 40% of the total travel, only 40 millimeter. So the 1 millimeter dead band in an installation will be 1/40 millimeter, 2.5%. Now, if the gain at a certain operation point is, for instance, 4, it means that just any moves between the two edges of the dead band will cause 10% jump in the actual flow rate. This is what you see all over the places, the valve hunting for position, going up and down, a couple of percentage all the time. We call it limit cycle, and this will result, for instance, boiler level fluctuation. Let's have an example. If you are running at 200 ton per hour and your process run 210 ton per hour, that's not going to happen, because the system will say, hey, give me more, 220. Oh, give me less, 200. Give me more, 220 again. So this is a typical sign what you can see. Now the big question is, the good question is, how could you find out if you have a problem, something like this? And there are typical symptoms. There are operational symptoms. So in this graph, this is from an Italian power plant. Over the 18 hours period, what you can see, the control valve didn't go too much above 50%. Okay, even at the highest load. It's still keep moving a little bit all over the place at the beginning, and you can see the control process variable, which is flow rate and level, is fluctuating all the time. And this is a clear indication. And also, what you can also see that as the valve goes to the higher opening, this fluctuation is getting better. So this is a typical symptoms that what the operator in front of the DCS screen can identify without any trouble, without any problem. So you can act to make it better. The other symptoms, what is typically seen by maintenance people, that the valve is leaking. Okay, now the valve can be leaking with multiple reasons. Okay, but if you see this erosion on the tip of the plug, the erosion at the bottom of the cage, that is really a so-called low flow erosion, which tells that the valve is spending excessive time below or near to 10% opening, and that's why erosion is happening. Also, if there's a cavitation damage on the tip of the plug, this is clearance flow cavitation, that also a good indication that the valve is oversized for the application. But all in all, I would say that if you have a control valve which need repair and you see get damaged more frequently than at least 5 years, that is a clear indication that there is an opportunity to improvement with a revised valve selection. Right. So there are symptoms easily identified. Now, if you think that this is something unique to the power industry, well, the thing is that based on a Chemical Process Magazine survey, which included 500 individuals from process engineering, procurement, operation, and maintenance, over 200 plants worldwide, they identified oversizing as the #1 control valve problem. So it is widespread everywhere. Now, just think about it. I know many people knows about problematic control valves in severe service application, but I wanted to highlight these 3 guys here: the feed gas control valve, the dilution steam control valve, and a fuel gas control valve on the pyrolysis furnace. These are pretty simple valve. I mean, there's not too high temperature, there is not too high pressure, probably there's no any noise problem either, but the main root cause of production loss on furnaces is the decocking interval wall, and the key application for that is a steam dilution ratio control. So this #2, okay? Again, nothing special valve, but can cause too frequent decocking interval. Also, to have an process optimization across the hot and a cold section is important in maximizing production yield, minimizing energy consumption, and complying with stringent environmental legislation. All 3 valves are contributing. No, so basically control valves has direct impact on a unit reliability, the process efficiency or safety, and for sure efficiency or production loss due to inappropriately engineered control valve can be extremely high, much higher than a proper control valve price. On the top of that, control valves are often work within demanding process condition. You can see risk of noise, cavitation damage, other premature damage. Now we're gonna look at some of these. Now let's start with the cavitation. So basically the physics behind the cavitation: when incompressible fluid, liquids, passing through a restriction, basically because they are incompressible, the velocity will increase. The smallest the diameter of the flow will be somewhere after the restriction. We call it vena contracta. Before then, the velocity will come down again. So the velocity profile in the restriction, like in the control valve, looks like this. It's increasing highest in the vena contracta and then decreasing again. Now, since Bernoulli law, we know that in this situation, as the velocity increasing, the pressure, the local pressure, will decreasing and then recover to the outlet pressure level. Now, so basically, this is the profile, pressure profile inside the control valve: inlet pressure, outlet pressure, and pressure in the vena contracta. If your pressure in the vena contracta go below the liquid vapor pressure, if it's water, let's say 150 degrees of Celsius water, vapor pressure 4.5 bar absolute. If you go below that in the vena contracta, you will vapor bubbles forming. And as the pressure recovers to the outlet pressure, these vapor bubbles will collapse, causing shock waves, and that shock waves will cause rough damage to the surrounding material, cavitation damage. Typical cavitation application: pump recirculation valve, boiler feed water startup regulator valve, or any attemperator spray water valve, really. If you look at deeply, basically what you can say that actually this cavitation problem caused by the valve design quite clearly. So yeah, if there's no restriction, there's no cavitation, right? But this is good news, because if we design the valve which has a cavitation problem, we can design a different valve which will eliminate the cavitation problem. And the strategy is that instead of having a big single pressure drop in the valve, we stage the pressure drop inside the cage, actually. So you got one pressure drop, a recovery area, another pressure drop, a recovery area, another pressure drop, to make sure we don't go below the vapor pressure at any point. Now, the number of stages depends on actually how much is the pressure drop across the valve. So this is the physics behind the cavitation. Any other explanation is rather marketing for a certain valve trim set. And I think you probably heard a different explanation about the cavitation, and you're probably thinking about, okay, this valve guy says this one, the other valve guy said a different one, which one to believe? And the good news is, actually on this, you don't have to believe me, because cavitation phenomenon is also well known and well explained in any pump manufacturer brochure. So if you open any pump manufacturer brochure, you will see exactly the same explanation about cavitation. Just as an example, here I highlighted cavitation occurs when the liquid in the pump turns to vapor at lower pressure. When cavitation takes place, bubbles are created at low pressure and liquid passes through the suction side, the impeller delivery side, the bubble implode, causing shock waves. So this is about the physics of the cavitation. And believe me, control valves, no physics, but country marketing brochure. So they will behave according to physics all the time. Now, once we are at the pump, let's have a look in this slide. What is really mean if your pump is failing? And in the middle section, you can see it starts with impeller damage and seal failure, excessive vibration, bearing failure, and that will develop environmental impact, for instance. So you've got some process leak, maybe fire or toxic release, or you end up with a production interruption, excess maintenance need, and if you are not lucky enough, you will make it in the evening news, get some fines, and all of those not good situations. But if from the middle now we start to look at the left, what we can see, the pump is cavitating, right? Why is happening? It says pump operating at less than minimum flow, right? Root cause, poor control valve leads to restricted discharge flow. This guy is a pump recirculation control valve. Now, a good pump recirculation control valve is still 10, 15, 20 times cheaper than the pump, and can kill the pump with a stiff upper lip, right? The other process change, suction pressure drop. Now, the net positive suction head of the pump, most of the cases, are provided by some tank, some column level, right? And that level in the tank or deaerator or column is controlled by some level control valve. Again, a valve can cause a serious damage. So makes sense to look at those properly. So when it comes to the pump recirculation valve, from application and valve engineering aspect, even if it doesn't cause pump damage, the not properly operating recirculation control valve cause wasted pump energy for multiple ways. So if the recirculated flow is higher than really needed, why? Because poor control performance forced the operator to set the set point far from the minimum flow. Everything what is more than really needed is pump wasted energy. Also, this valve are supposed to be closed with a very minimum leakage when the unit is running, right? Leakage causes continuous flow erosion to the valve trim. In this critical application, combined with cavitation, and it's getting worse and worse and worse. Leakage wasting pump energy, but causing valve damage and more frequent repair. And if you are not lucky enough, cavitating leakage can potentially damage the downstream pipeline as well. So while the applied solution can be different in size and capacity, there are some basics to consider. High pressure drop means proper cavitation abatement is necessary. Accurate controllability, as low as possible minimum controllable flow. The higher the rangeability of this valve is better. So linear inherent characteristic is a no-go, despite many originally installed recirculation valve are in a linear characteristic. And class 5 shut-off to minimize the leakage. The other cavitating application, produced water system, for instance, is the discharge pressure control valve. Now, on the top of that high pressure difference, there's quite often see impurities in the liquid, in the produced water. So this is an example where the originally installed competitor valve gave up the fight spectacularly. The challenge was, reasonable high pressure drop combined with entering particulates, and those particulates just blocked up the bottom end where you had a more severe cavitation protection, and then the top end of the cage just couldn't control cavitation anymore. Now, for this kind of application, apart from based on our global engineering expertise, we have a dirty service stream, which is a multi-stage cavitation abatement stream. So when our colleagues get hold of this case, they analyzed the conditions. They quoted Fisher HPT valve with a dirty service stream. This dirty service stream first has a protected seating area, which provide long-lasting tight shutoff, and also designed with a combined axial and radial flow pass with large opening. It can pass through up to 3/4 inch of diameter stones. So that stream was installed. It's a case of with an oil sand producer in Alberta. So the DST stream was installed in January 2006 and is performing well ever since. When they pulled out for regular maintenance, they cleaned and they found the stream completely intact. So when it comes to Fisher cavitation abatement portfolio, we have a very large range for clear fluid on the top or for dirty fluid on the bottom, and also even for rotary valves as well. These are highly customizable and can provide the best fit for your processes. If we move to the upstream separator applications, there are critical valves all over the place. Each and every has a direct impact of the separator efficiency and safety. Now let's look at the high pressure separator level control valve. So control the produced water interface level in the HP separator, and it delivers the water to the overboard system. It can flashing. Now we are talking about flashing. So what is flashing? Basically, if we go back to the pressure profile in the control valve, what you see that this green line, after it's recovered to the downstream pressure, is still below the vapor pressure of the liquid, because the downstream pressure is lower than the vapor pressure of the liquid, which means that the bubbles forming, but won't all collapsing, but downstream will travel a mixture of vapor and liquid at the outlet. So I said control cavitation was caused by the restriction, the valve itself, but flashing is due to the process. Whatever valve construction you put in here, flashing cannot be eliminated. Only can be find a construction which can deal with that or survive. So based on, again, real process condition, a reverse flow rotary valve or a different angle valve solution could be a solution for long-lasting flashing valve. And also flashing shouldn't be confused with outgassing. Flashing is a kind of erosion. So erosion always got a fluid factor regarding to the medium, and the material factor regarding the material what's being used. A typical erosive application is the quench tower level control valve. So the cracked gas need to be quenched to avoid excessive cracking. And this valve is remove the heavier hydrocarbon from the cracked gas before that goes to the compression. Now, in this construction, the V500, what you can see as the plug moving from the fully closed to the fully open position is offset, so it's moving away from the seat area, which helps to avoid any particulate to stuck between the plug and the seat, and also reduce the erosion. I mentioned outgassing just before. So outgassing is different to flashing. In outgassing, you've got entering gases in the liquid. So actually, the inlet of the valve is liquid, but this entering gas, as you drop the pressure across the valve, will escape from the liquid, and then downstream to the valve, there will be a two-phase flow. Now here you've got a two different constituent. It's a mixture of some vapor and some liquid with the multiple molecular weights are present. So that is different to the flashing. Typical application again, reach-amine let-down valve, which is widely used process to remove acid gases from the cracked gas. So lean-amine absorbs impurities, and then this reach-amine let-down valve maintain the level in the absorber and facilitate the pressure drop into the flash tank downstream to this valve. The challenges with outgassing that probably the biggest is to clearly understand the gas volume ratio at the downstream of the valves. It's really important to get an accurate customer specification sheet to calculate, because this kind of calculation isn't really included in a different valve sizing standards. So we have to have a very detailed look on that. And the proper process data is just crucial. Also, you'll see a reasonably high pressure drop here. You might have corrosive presence, and noise and vibration can come. But based on what the calculation will show, we can offer a different solution. Again, a wide range coming from a drilled hole cage flow up to the more and more tailor-made specific trim set. The next concern about the control valve is aerodynamic noise. The preliminary source of aerodynamic noise is a compressible fluid turbulence. There are two locations of interest. First is a throttling region, where the fluid pressure is low and the velocity is high. The second region is a location between the control valve trim and the body valve, where again high-speed fluid impingement can result high turbulence. And the third location, if you like, is at the outlet of the control valve. So basically, since 2010, it's clearly identified that we are talking about two separate noise source. One is a trim noise, and which depends on the type of the trim and its geometric features, and the valve outlet noise, which depends on the outlet area, outlet Mach number, and the expander downstream the valve. Before 22, it wasn't put in a standard properly, and there were some different approaches by a different manufacturer, just to say the least. Right, the typical noise application: vent to flare, separator pressure control valve, compressor anti-surge valve, export steam pressure reduction valve, and steam vent valve. Obviously, if you just pick the high pressure separator vent to flare valve, this is intended to operate only in emergency situation, a kind of control safety. It takes considerable pressure drop, and you want to minimize the leakage when it's closed, because unwanted leakage is a direct waste. Now, these often selected only for the maximum flow rate during the original project phase, and often installed with linear characteristics trim. Again, as we saw, the linear characteristic isn't very good to do fine control lower opening, so the operators need to move the set point far away from the necessary value. Similarly to oversized valve, it has a risk of low flow erosion damage to the plug. And +5 shut-off is highly advisable. As I mentioned before, the calculation method for order installation didn't include additional noise generation at the valve outlet. So you might have a valve with a noise reduction trim, but you still might experience elevated noise level. Also, just to show the difference between the linear and an equal percentage characteristic, inherent characteristic valve, the same capacity on the linear characteristic valve happens at, let's say, 10% opening, while in the equal percentage characteristic valves happens around 40% opening. And also what you can see, the gradient of change of the capacity is less steeper in the equal percentage characteristic valve below some 60% opening, which means you have a very nice and smooth capability to control, and also you have a very nice capability to control much lower with an equal percentage characteristic. It is very important that in case of valve replacement, always need to check the original process data versus the real site operational cases, because that makes a difference. Now, what can you do with a noisy valve? Well, there is one way to look at, which is called pass treatment. So you can see that, for instance, in this example, you'll get a standard Schedule 40 pipe, and you measure 110 dBA. If you increase the pipe schedule, you have a heavier pipe valve, your noise reading will come down. If you wrap around some insulation, acoustic insulation, your measured noise is coming down even further. However, it is only muffled the noise and vibration is still there inside the pipe. So if you return to standard schedule, your 110 dB noise will come back again. Okay, so you can use some of these to reduce from, I don't know, 90 dBA to 85 dBA, but in reality, when it's getting more and more a noisy solution, you really need to do a source treatment. A source treatment will treat or eliminate the noise from generation inside the valve. The idea is to create smaller jets at the outlet of the cage, which will shift the frequency above the audible zone. The dBA measurement doesn't consider any frequency above 20,000 kilohertz. Also, you have to make sure that the jets are separated at the exit of the cage. So for that, we've got a Whisper 1 or Whisper 3 drilled hole cages. Now, the thing is that as the dP per P1 ratio is increasing over the valve, the originally separated jets start to grow and recombine and will act as one single big jet and will get noisy again. So to tackle with that, we can change the spacing between the hole, or we can use smaller hole, or we can do both of them. So this is how our Whisper 3 drilled hole cage works. We also have a Whisper flow technology where you have an additional pressure staging. So as the medium gas or steam enters the cage, there is one pressure drop, right? Then there is some expansion area, and then there is another pressure drop as it exits the cage. And you can see also the outlet area. At the outlet, the jet separation still takes place. Sometimes people confuse this trim with some competitors' torches pass kind of trim, which is admittedly pretty different. And also we have noise reduction solution for rotary valves as well. The one new thing is the Whisper Fisher 6060 Whisper tube model attenuator. Now, this is an interesting unit because basically it helps you reduce the noise without interfering with the process. So basically, you can, if you have a noise problem, you can install this in a place of a spool pipe piece, right? This is a full bore pipe basically, so the pressure drop is negligible. However, there are internal cavities, right? Differently made internal cavities which produce acoustic wave reflections and reduce the noise propagation downstream to this unit. And it can be fitted after a noisy valve of yours. If you don't want to touch the valve, fine, you can install it after that, and you still reduce your noise, or after a compressor or any noisy location, really. So you don't have to really stick it with a control valve directly. One more important application is a compressor anti-surge valve. So basically, a surge is happening when the flow rate through the compressor is restricted. So the downstream pressure starts to increase to the point when the impeller is decoupled and cannot push the flow forward anymore, which means then the gas starts to flow backwards, and then the outlet pressure drops again, so the compressor will push forward again, and this cycle will start. It's a very quick cycle. The duration is between 0.3 or 3 seconds. And it will cause compressor vibration, temperature rising, and eventually will do damage to the compressor. Now, on a compressor on a wheel map, you can see the surge line, right? And this is the line what you don't want to cross. So basically, the anti-surge valve is making sure that when you are getting close to the surge line, the valve will open and let across a compressor a more flow rate to make sure it doesn't go to surge. And really the goal is to avoid any process instability, any potential machine damage, any trips, and also the better or the more accurate is your anti-surge valve, you can take a lower control margin. Control margin is basically this green line. So if you can have a better anti-surge valve, you can move it closer to the surge limit. So there is a bigger area where you can use your compressor. Now, a compressor anti-surge control system is taking a lot of measurement, which go to the controller, and based on those measurements, the controller will send a drive signal to the control valve to move. A typical requirement of nowadays for the anti-surge valve is less than 2 seconds stroke time to open under positional control, less than 1 second stroke time fully open on a solenoid trip valve. But these valves are big, so this is an example where you have a very big anti-surge valve because you need a lot of capacity time to time, and still you need to make sure that you open very quickly. You also want to make sure a minimal under and overshooting because the resolution and linearity and deadband is getting more and more important if you want to control as close to the surge limit as possible. Now, the traditional setup would include on the hookup of the actuator a lot of accessories, volume boosters, quick exhaust, trip valves, and so on and so forth. Altogether, some 18 accessory, right? And you would get the step response out of that with a big overshoot and undershoot and overshoot and undershoot. And this over and undershooting really what will then limit you how close you can go to the surge limit. Now, we are offering the optimized control valve with ODV package for anti-surge application. These are custom engineered and factory tested complete control valve solutions. One-handed valve body is a special design to meet the requirement, and then the digital valve package is a special design compared to suit the best to the actuator itself. And so the ODV package includes much less number of accessories. So instead of 18 accessories, now we have five accessories, which immediately improves or reduce the likelihood of failure. Okay, and also with fine tuning on the DVC positioner, you can have a very nice step response diagram without any over and undershooting at all. Now, also important to make sure that you understand how your valve health is improving over the time. So we are offering a tiered kind of valve health monitoring. The advantage, the advanced diagnostic is for valve wear, which has very high impact on the unit efficiency, or for valve which traditionally has periodically scheduled maintenance. So you can run a total scan of the valve when it's out of service. So you create some graphs, and you can compare to the graphs what you take in a year before, 2 years before, on any time earlier, and you can see any deviation between the earlier and the current graphs, which will clearly indicate if there is a need for repair or not. So it can help reduce the maintenance cost and time. The performance diagnostic, on the other hand, are for the valve which can cause serious production disturbance if they break down. Performance diagnostic communicate with the asset management software, continuously monitors the valve, and send warning to the control room, so you can learn and act on the valve problems as early stage before bad impact happening. Emerson also has in Marshalltown, Iowa, an innovation test lab center for Fisher technology, where we can evaluate our control valves, can do design verification through lab testing within realistic situation with very high pressure, high or low temperature situation. We can test cavitation, material fatigue, and all of those, which we can learn and improve our valve design if needed. And this is a place if you have a chance to visit. As a summary, Emerson Fisher control valve portfolio is wide and developed together with the industries since 1880. We have deep industry process expertise, and we can offer control valve solutions to best fit your applications. We thoroughly test all new technologies before we bring it to the market. We can provide tools to have a peace of mind about your asset performance. So don't hesitate to reach out with any control valve related difficulties. This is my email address. Thanks for listening. And is there any question? Please shoot.
Yeah, thanks, pal. Very interesting topic. A lot of detail covered within. I'm going to open